great pleasure to welcome all of you to the lecture by Dr. Radhakrishnan, an eminent space scientist and a former chairman of the Indian Space Research Organization and the Space Commission of India. This is to commemorate the 116th birthday of R D Tata, whose association with TIFR began with his writing a letter to Dorabji Tata Trust, requesting them to support the dream of Dr. Homi Bhabha in building a school of physics comparable to the best in the world. These two visionaries, with the active help from the then Prime Minister, Pandit Jawaharlal Nehru, created the Tata Institute of Fundamental Research, which was to later become the cradle for the Atomic Energy Commission of India. Mr. Tata's association with the institute, which began with the creation of Tata Institute of Fundamental Research, ended only with his death in 1993. Though TIFR became a deemed to be university only in the year 2000, enabling it to award its own degrees, it had been accredited to the University of Mumbai, from where students of my generation got their PhD degrees. With a small group of alumni, TIFR Alumni Association began in the year 2000. The association serves a medium through which people who have passed out from TIFR, people who had been faculty of TIFR, they keep in touch with their alma mater. Last year, TIA organized the Golden Jubilee function of the first graduate school that was established in this country in physics. TIA provides support to the TIFR Alumni Fund, as well as organizes periodic lecture. Today's lecture on Mr. Tata's birthday began with the first ever lecture in this series given by Professor Yashpal in the year 2002. And that year also it was given precisely on his birthday, July 29, year 2002. I now request our patron, Director TIFR, Professor Sandeep Trivedi, to speak a few words on this occasion. Professor Trivedi.
Myself. Yes, thank you very much. Can you hear me?
Yes, now yes.
Dr. Radhakrishnan, Professor Ghosh, Professor Ravindra Kumar, all my dear friends who are here virtually with us, and especially our friends from outside of TIFR who are joining us on this occasion to hear this lecture. And I extend a special warm welcome to the students who are tuning in to listen to this lecture today. It's a great pleasure for me to welcome you all this evening to TIFR. We are indeed very fortunate to have Dr. Radhakrishnan with us to give us a lecture on this important occasion. As Professor Deepak Ghosh has already mentioned, Mr. R D Tata was really quite a remarkable visionary, I would say. Of course, he's very well known as an industrialist, but he also had this real passion and commitment to grow science and technology in India. And that's really very noteworthy. As Professor Deepak Ghosh said, it was the coming together of these three extraordinary individuals, Dr. Bhabha, Mr. Tata, and our visionary first Prime Minister Pandit Nehru, that led to the creation of TIFR. But Mr. Tata's association, in a sense, only began with that. He was the chairman of our Council of Management for several decades. And, I never used to know what role the Council of Management actually plays in our institute till I became the director. But then I saw what an important role it plays, and I got to read some of the minutes of earlier meetings and Mr. Tata's intervention. And what struck me was the level of the attention to even sometimes minute aspects of the institute, year after year, that he brought. So it was a real commitment from his heart. I think as a mark of that commitment for science and technology, he also served for many years on the Atomic Energy Commission of India. Again, with great, real attention to all kinds of matters. So he was really an extraordinary individual, I think, and it's a great privilege for us to celebrate to the day, actually, as Professor Ghosh said, his 116th birthday today. I congratulate the Alumni Association for bringing together this lecture, and that too precisely on Mr. Tata's birthday. I'll just say a few words more. Dr. Radhakrishnan is, of course, very well known. He was a chairman of the Indian Space Commission, has played a very important role in taking forward science and technology. I just learned that he's the chairman of my alumnus, IIT Kanpur, and it's a matter of great pride for me to have heard that. So I think we are really privileged to have him as our speaker today. The choice of topic is also indeed very appropriate, because Dr. Sarabhai, of course, is another great visionary when we think about science and technology and its growth in our country. His birth centenary, as many of you know, was last year. And so indeed, it's quite appropriate that we remember him also today. And in fact, he too had a very close association with our institute. As some of you know, he was the chairman of the Atomic Energy Commission. But even before and after, he continued to be involved with the institute. I'll give you a small example of his role. At some point, an important radar system needed to be put in place by the Air Force. And the Prime Minister inquired from Dr. Sarabhai which organization could do it. TIFR's core mandate was pure science. Of course, we were involved in atomic energy, but Dr. Sarabhai responded, I'm told, nearly immediately that it is TIFR. TIFR should be entrusted with the task. And that is how the famous radar project came to TIFR. I'm happy to say we delivered on it. I was quite, it was interesting to learn that actually some parts of the system continue to be used today by the Air Force. And out of that experience in radar technology then came our experience in general with telecommunications and so on. And later on, when CDOT had to be founded, some of our scientists went and played a key role in that. So Dr. Sarabhai's hand in sort of guiding aspects of TIFR's growth can be seen, even when you look long-term as to how TIFR has grown and how it has managed to contribute in whatever ways we have to the country's development. So it's indeed, we are very grateful to have Dr. Radhakrishnan with us and for his excellent choice of subject today. I really look forward to his talk. I'm sure it'll be interesting and also very inspiring, especially for all the students here in the audience. So I welcome Dr. Radhakrishnan and welcome you all to this lecture this evening. Thank you.
Thank you, Professor Trivedi and Professor Ghosh. Now, it's my great pleasure to introduce our speaker today. Dr. Koppillil Radhakrishnan is a widely acclaimed national figure, having achieved tremendous success as a leader of many of India's space missions, including the Chandrayaan-1 and the Mangalyaan. Under his leadership, India made tremendous leaps in space technology, from launch vehicles all the way to planning for human space flight. His inspiring leadership led to the successful Mangalyaan mission. In the very first attempt, executed in all of 4 years, at the lowest cost anywhere in the world, a fact that our Prime Minister repeatedly refers to in his speeches to global audiences as a mark of India's technological prowess. An engineer by training, he received a PhD from IIT Kharagpur. The boy from Irinjalakuda, as he is known in Kerala, joined ISRO in 1971 and rose to lead the organization during 2009-2014. During that period, he led as many as 37 space missions. I repeat, 37 space missions, including the historic Mangalyaan. He has won numerous awards. In fact, it would take a long while to list out all the achievements and all the awards that he has got. But suffice it to say that the country honored him and honored itself by bestowing the Padma Bhushan in 2014. If you think Dr. Radhakrishnan is a tech man, only technology, that's again not true. He is a multidimensional personality. I was very pleasantly surprised and impressed when I saw him once on television talk about his classical music singing. So he is an accomplished classical vocalist, sings regularly at concerts, and not only that, he's also an acclaimed Kathakali dancer. And so it's remarkable that one person can straddle the seemingly disparate realms of technology and arts with consummate ease, without worrying about which is which. So that's something very unique in Dr. Radhakrishnan. It is fitting that we have today a speaker of his eminence, as we remember another great son of India, Mr. R D Tata, one of our founders and early mentors. Ladies and gentlemen, I am privileged to invite Dr. Radhakrishnan to deliver the R D Tata Lecture 2020. Over to you, Dr. Radhakrishnan.
Thank you. Good evening to all of you, Professor Deepak Ghosh, Professor Sandeep Tiwari, Trivedi, Professor Ravindra Kumar, and Professor Deepak, Fatak. I'm extremely privileged today to be talking to this erudite audience, even though I miss their physical presence. But I can just visualize several people around who made TIFR proud, who are going to make TIFR proud, the young generation around. I have a few slides to talk about. Before that, let me also join three of you in paying respects to the great legendary R D Tata. He is known as the father of civil aviation in India. He was also chairman of Tata Sons at the age of 34. It is something the younger generation should take note of. He was an entrepreneur, but a value-based entrepreneur. And that is one of the USP of the Tata family of industries today. And an admired institution builder, the Indian Institute of Science, the Tata Institute of Social Sciences, and TIFR are three glorious institutions keeping that legacy forward. If I can have the first slide, I'll just take on from where you left about the legendaries of Indian science and technology who made what we are talking today possible. Like you said, TIFR was the cradle for the nuclear program. The physical research laboratory was the cradle for the Indian space program. It all started in 1962, and the great combination of Dr. Bhabha and Dr. Sarabhai made this possible. And the famous picture of these two visionaries selecting Tumba for starting the sounding rocket launching station. It is something historical. In 1963, November, the first sounding rocket took off from Tumba, and that was the physical birth of the Indian space program. And what you see next is the spirit of self-reliance that Dr. Sarabhai showed by setting up the Space Science and Technology Center, and then the experimental satellite communication Earth station, one at Tumba and one in Ahmedabad. These were two pillars of the space research in the 60s. And what Dr. Sarabhai provided to ISRO was an indomitable vision which is spelled out in 1968 at Tumba, when the rocket launching station was dedicated to the international community, to the UN. From an INCOSPAR, a committee on space research nucleated in PRL, the ISRO was born in the year 1969. And the international reach of Dr. Sarabhai and of this startup ISRO is something commendable even at that time. And we had associations with leading space agencies of the world, especially France, to quote an important agency. Self-reliance, that was something which was imbibed by everyone. And Dr. Sarabhai created a network of institutions in Thiruvananthapuram and in Ahmedabad. And the programs in rocketry, the Rohini series of satellites, rockets, and applications program, all were envisioned. Early studies for the INSAT program started. There are 5 papers written by Dr. Sarabhai. There are visions in each one of these areas, in communication satellite, remote sensing satellite, space science, rocketry, etc. 1971 December, he departed, and we got another legendary to take the mantle of the space program, that is Professor Satish Dhawan, who was then a member of the Atomic Energy Commission. And Atomic Energy Commission was at that time guiding the space program too. So the Space Commission got formed in 1972, the Department of Space came, and ISRO became part of the Department of Space. Physical Research Laboratory also became part of Department of Space. But what is unique in this transition is here is a successor who said, it was Vikram's vision, I only executed it. And that was probably a very humble way of expressing the transformational execution of the space program that Professor Dhawan did for the next 12 years. Generally, I say the character of an organization, the outlook of an organization is molded by the founders. And these 2 legendaries coming in that sequence made ISRO what it is and ISRO culture what it is. Can I have the next slide? Can I have the next slide? Now we just look at what happened over the last 6 decades in the space program, where we started, where we are. Initially, the Rohini sounding rockets were developed, launched from Tumba with scientific experiments from TIFR, from NPL, from PRL, and universities. The 3 major programs that came in the beginning, they were the SITE, SLV3, and Aryabhatta. One, to show to the country that satellites can be used for several applications. The second one was to make a satellite and get it launched. And the third one was to develop a rocket. It can put a satellite into an orbit around Earth. And we also should remember these 3 programs were guided by 3 legendaries, Professor Yashpal, Professor U.R. Rao, and Dr. Kalam. And that is our foundation. I just put here a few dimensions of that space program. The simple one is to talk about the numbers. We have done till now nearly 180 space missions, rockets and satellites together. The numbers are increasing. Each decade, if we take from 20, we went to almost 40 and almost 100. And we had a great partner, that is Indian industry. Almost 150 of them are working today with ISRO. But qualitatively, in terms of technology, in terms of science, how did we progress? From the Aryabhatta satellite program, we got into a few more experimental satellites, but India got the INSAT-1, a multi-purpose satellite conceived by us, but procured from abroad by 1983. And we also built a national space system around INSAT. And that was one of the dreams or the vision of ISRO to use the space system for finding solutions to the problems of society and development. So INSAT system was born, and then we also had the INSAT-2, which was built by us, an Indian satellite system. INSAT-2A and INSAT-2B came somewhere in 1992-93 period. There were several communication satellites built, and we came by 2005 with a new class of satellite called INSAT-4, which introduced the direct-to-home service in India. And if you look at the two, INSAT-2 and INSAT-4, on one side, we had a 5-watt SSPA being used, and here there is one with almost 140 watts TWP. That's the level of power. In terms of EIRP, from 35 dBW to 52 dBW. An uninterrupted service. This is what was demanded for the DTH. And currently we are at GSAT-11, a new generation of satellites. They are called the high throughput satellites. And here we talk in terms of the data rates that it can handle. And GSAT-11, which was launched in 2018, has a data rate capability of something like 16 gigabit per second. We were handling in the INSAT-1, INSAT-2 days, the C-band transponders, S-band transponders. We got into the next level KU band, and in GSAT-11, we are at KA band. And this is something technologically very important, capacity-wise very important. The GSAT-20 that is getting ready to be launched can handle 36 gigabit per second. Where do we stand with respect to the international community? Internationally, the best satellites of communication today can give about 100 to 120 gigabit per second, and we are moving into that direction. They are satellites of 6 to 6.5 tons, dealing with power output of 15 plus kilowatts. So this is the kind of progression that has taken place in the communication area. Side by side on remote sensing, we started using the Landsat satellite system to prove that it can be used for several applications. And I must again talk about the colleagues of TIFR like Dr. George Joseph, who have done yeoman work in this area to make the imaging sensors. IRS-1 got ready by 1988. It was orbited, and that became the bulwark of our remote sensing satellite system. Many follow-on satellites were there. By 1995, the IRS-1C with the 5.8 meter spatial resolution became the best commercially available remote sensing satellite in the world. And people from US and Europe started receiving data from IRS-1C commercially. Post-Kargil war, India got into the high-resolution satellite system. It's called TES. And then came the Cartosat series of satellites. From 1 meter resolution of TES, today we are at Cartosat 3, which has a spatial resolution of 0.26 meter. That is less than a feet. But they are all satellites with optical imaging systems. And for this country, microwave remote sensing satellite is quite important if you want to study the agriculture. Under cloud, what happens to the crops? Under cloud, what happens to the flood affected areas? And came the RISAT-1, the first microwave remote sensing satellite of India in C-band. And there are a few more in other bands coming up now. And one of the satellite which is going to be done by NASA and ISRO together, called NISAR, will have again microwave remote sensing payloads. A new thing that came in the last 15 years is the navigation satellite system. And we are all used to the global positioning system of US. We know about the GLONASS of Russia. We know about the Galileo of Europe. They are global systems, but NAVIC is a regional navigation satellite system of a constellation of 7 satellites in the geo orbit at 36,000. Some are on the geostationary orbit, some are in the inclined orbit. And the most important part of NAVIC technologically is the timing system, the atomic clocks which are on board the satellite and which are there in the ground stations for the reference. We have been using imported clocks and we had also problems. But at the moment, ISRO is getting ready with an indigenously developed clock, which I would imagine will fly soon. Now, if you look at the launch vehicle area, we started with SLV-3. In 1980, we had the first launch. We proved that we can orbit a small satellite. We had a difficult phase of going through the ASLV on several technologies related to the launch vehicles. We learned what it means when a vehicle goes through the dense atmosphere and when the dynamic pressure comes. We learned how to precisely inject a satellite into the orbit with closed-loop guidance system. And PSLV had one more new technology, that is the liquid engine-based stages. So far, we were mastering the solid stages, solid propellant stages. So PSLV was a combination of heavy solid booster, heavy liquid stages, closed-loop guidance system, and several other mechanisms. We had to raise the power of PSLV from its 1 ton to an orbit of 1,000 kilometers to almost 2+ ton to a geostationary orbit of 36,000 kilometers. And logically, we needed to go for a more efficient propulsion system, and we got into the cryogenic propulsion system, which is complex, which has a lot of paraphernalia to carry, but the specific impulse that it provides is far high compared to what a solid liquid stage can provide. So we have an efficient vehicle. We took almost 18 years to fly the cryogenic stage. First one failed, and the second one was a success in 2014. And till now, all the GSLVs flown with the Indian cryogenic stages have gone so well. The next step was to have a vehicle GSLV Mark III, a 4-ton satellite into geostationary transfer orbit. That is the target, and we achieved that, again, with a more powerful cryogenic engine. In fact, GSLV Mark III was used even for the Chandrayaan-2 launch that took place a year ago. Comparing internationally with other systems, where does GSLV Mark III find a place? Where does PSLV find a place? Where does GSLV find a place? PSLV had 45+ successful missions. Highly reliable vehicle sought after by international community. It has launched satellites of nearly 30 countries. Some very remarkable satellite systems like Spot 6-7, and there are several small satellites. If you take GSLV Mark III of 4-ton to geostationary transfer orbit, can be benchmarked with other satellite launch vehicles of the world. And I will use a number, the tonnage it can provide into a low Earth orbit. For GSLV Mark III, that number is 10 ton as it stands today. The Falcon Heavy of SpaceX has a capability of 65 tons to low Earth orbit. Long March 5 of China can put about 25 tons. The Ariane 5 of Europe has a similar capability. And there are plans to enhance the launch vehicle carrying capability by introducing a semi-cryo engine and stage in the near future. Technologically, again, what happened in this launch vehicle area is by 1999, we started getting international customers and we started flying multiple satellites in the same launch mission. Started with 2 and we got up to 104. Technologically, what is important is a clean separation and to ensure that these satellites don't collide. We also had a unique experiment in 2007 that is the re-entry of a capsule from the orbit, done very precisely. And that module is still sitting in Tumba in the church building exhibition. To this audience, I don't want to speak much about AstroSat. But to recall in 2012, when we had a post-war meeting in Mysore, the international astronomy community came and told for the next 5 years, AstroSat is going to be a great contribution for the global astronomy community. And what you have done is exactly that. You have achieved that. Instruments which are either state-of-the-art or some of the instruments which are even superior to what you see from other space agencies. 2 examples which came to my mind, which I have seen along with your colleagues, is the UVIT, which has got a better space resolution compared to the NASA equipment. And if you look at the energy range of another equipment, it again is quite wide. And they are giving class results, and this community should be really thanked for making such a wonderful set of scientific instruments. Chandrayaan-1 was our first step beyond Earth, and what we learned several things. The harsh environment that any satellite has to go through in an orbit around Moon, number 1. Number 2, how to capture a lunar orbit. How to have a deep space mission, and at that time that was the deep space mission. 4 lakh kilometers was a deep space mission for us, and we had the ground station. And of course, it was an international mission. We gave opportunity for several other space agencies to put their instrument, and good results came out of Chandrayaan. Mars orbiter was mentioned, and what we learned at that time, how to traverse a much, much larger distance, how to navigate precisely to capture the Martian orbit, how to manage the spacecraft when it does not have any visibility with the ground station by providing autonomy into the spacecraft system. And it has worked beautifully. And the Mars color camera that it has given very good results. It was a technological mission, but it has also given a little bit of science. Now, this is where we are standing today. What are we in terms of technology? Where have we excelled in applications? I will just take a few minutes to talk about that. Next. This is the multidisciplinary capability that Indian space technology has achieved over the last 6 decades. We talked on many of these areas. But what is more important there is what is written in the 4 corners. The shared vision that ISRO India had. Dr. Sarabhai's vision, shared by his successors and the organization. But we didn't stay still as our capability got enhanced, as the world changed, as our aspirations went up. We went to the next step of Chandrayaan. In 2010, we ventured into Mars exploration, and presently we are into the human space flight. ISRO stands for Team Excellence. We generally say when we join ISRO, the I is given to ISRO, and what the team makes is more important rather than what I did. And that works. And at the bottom, I have written again 2 small bullets of the similar nature: space technology, launch vehicles, and satellites are large and complex systems, and risky. Failures are common, and we learn from failures. But the organization is resilient to the failure, and we come out of it. It's part of our life. Next one. Next slide, can I have it? Yeah. This has been our focus area from the beginning. And this is where India has been a model to the whole world. Space applications, communication, infrastructure for the country, starting with the INSAT-1 system, data connectivity, broadcasting, and education, the kind of inroads it has made into. Monitoring of natural resources, meteorological observations, which it provides to the India Meteorology Department, and our studies to understand the climate and environment. Strategic services is something which came over the last couple of decades. Now it has an emphasis. The NAVIC provides the assured navigation signal for the country. Assured is more important there. And location-based services which are enabled by the combination of the three sets of satellites. And geospatial services and development planning, and more importantly, the disaster management support that India is able to get. The moment the cyclone comes, everyone is ready. There is a precise forecast by IMD, and we monitor the system using the satellites, and the parameters required are provided through the satellite system, and we are at it today. What made this possible? It's on the left side. The users have been in the loop in configuring the satellite system and also in using them. The capacity of the central state users and those in the industry who deal with downstream services have been enhanced. These were the activities of the 80s and 90s. Then came the institutionalization of these systems in the various ministries. And I must say, in 2015, in Vigyan Bhavan, there was a major meet taken by the Honorable Prime Minister, that all government departments of Government of India and the states were telling what they need and how they can use the space systems for their governance development activities. The next logical step has been externalization. And we started doing this with the Forest Department, with the Ocean Department, with the Agriculture Department. They all have their institutions to deal with the space applications. And today there is an institute, Gujarat also for doing this. Is a continuing process. And the space systems with the new services will come always, and the system will develop. Next. This is where India has been. Over these years, how the world has changed from bipolar world. We are now in the multipolar world. The dynamics has changed quite a lot. Today, there is cooperation and there are joint missions being done, being planned. There is also a global exploration strategy worked out by 15 space agencies, talking about a program from now to 2040. There are 72 government space agencies today in the world. And the new entrants, like the UAE Space Agency, who launched a satellite to Martian orbit, they are the one at the frontiers. If you look at the economy of it, it's about $366 billion US, the global space economy. And much of it comes from the commercial system, almost 75% of it. And if you take this total 366, 70% of it is from ground equipment and space-based services. The launch and the satellites will take about 5%. There are today about 2,100 operating satellites, but you will see one phenomenon. Many of them are small satellites. It's a new technology trend which has come up now. And new technologies like 5G, they supplement and complement and sometimes compete with the space system. This is a continuing process. Space Force is the fourth dimension today in the military activity, is already in place in US. Cyber threats are expected when the satellite systems are going to be part of our life in civilian and military dimensions. Debris from the parts which are getting out of the active satellites, something close to 20,000 parts. At high speed they go and they try to trouble the satellites which are really operating. A new dimension that the astronomers are now worried about is with Starlink, with the OneWeb, having many satellites in orbits around 500. What happens to the astronomical observations? Again, what happens to the physical collision? So these are some of the things which today one has to worry about. And of course, space governance becomes important when so many players are in this direction. When the space started in 1950s, what is called a modern space age, there were two players, US and the Soviets. But today there are a different kind of protagonists, the SpaceX. The Falcon Heavy of 2018 put a payload vehicle towards Mars. The Dragon was a commercial spacecraft which delivered the US NASA astronauts into the International Space Station. The Starlink is just building. Rocket Lab is a gentleman who talks about frequent and low-cost access to space. And they're able to make at least a few launches. And Blue Origin, another company, which is now contracted by NASA for a moon lander for their Artemis mission. And Virgin Galactic talks about space tourism. The important part of it is there are private players in space. They are industries. They take contracts from the major space agencies and they do their activity, whether it is Boeing or Lockheed Martin, etc. But here there are protagonists who have put their money and they are venturing into the space activity. And there are several startups, and this is the new space age. Now, overall, where India stands in the global scenario of the 72, the order today is US, Russia, Europe, Japan, China, and India. From 2007 to 2014, there was a global agency called Futron in US, which was making this benchmarking every year. We have been at 6 or 7 there. There have been also agencies which have done this quantitatively, looking at the capacity of each rocket, the reliability of each rocket, and the satellite, etc., in various portfolios. India is there. Now, India has to be there in the future too, in a rightful place, not at 6, but in a better place. And recently what has happened in India is the structural reforms, bringing the private players as co-passengers in the system. And also more liberal data policy. Next one, can I add? Next slide. These are the 5 E's of the new space age, which I tried to push. The community which is looking at the science, the excitement, they have enough in plate for exploration and also exploitation. Exploration of the solar system, exploration of the universe, study about the life, understanding the cosmic hazards, which are again important when we talk about the deep space missions. A new dimension has come. Why we go to Mars, why we go to Moon? What about the asteroids? Can we look at the celestial resources? What needs to be done downstream in our place to utilize them? What is the time frame? Maybe 50 years. How to use the solar power satellite systems? This is another area. Habitat in space, there is one country which talks about a township after maybe 100 years in Mars. It may be a dream at the moment, but that's a direction. If you look at the enterprise part of it, we talked about 2,100 satellites of different dimensions now. These are space assets. They have to be built, they have to be launched, they have to be operated, they have to be safe there. The ground systems required for all of them, and even the operation of the space station or the space tourism, etc. These become part of the enterprise that is corresponding to that 366 billion US dollar. The most part of it where India has excelled, India has become a role model is on the engagement. How the space can be used for human well-being. Today, globe has got a sustainable development goal, SDG 2030, which talks about all areas and at least 12 of them require space in a major way. Space has become an instrument for security, for surveillance, and superiority. And the space governance becomes important. All this can be done only when the technology is ready. And when we are talking about going to Mars and bringing cargo from there back, it requires launch vehicles of the class 150 to 200 ton to LEO. Today's best in the world is 64 ton to LEO. What is being done by US now is space launch system with 130. So there is a requirement for larger capability. Return flights of the human beings, return flights of the cargo, space robotics, and the deep space gateways around Moon, around Mars. So these are all the broad directions for the technology for the future. The last slide I will just put, next one. This is basically India's new frontier into the space exploration. Gaganyaan is the beginning of the human space flight. There are several complexities. I'm not going to dwell much on that. But along with the human in loop, there is also a need for cognitive space robotics, which will help us to explore Moon, Mars, asteroids, and other parts of the solar system in the future. I will stop at this moment and then probably you could have a few questions or interactions as it goes.
Well, thank you, Dr. Radhakrishnan, for an excellent talk. And I think the history of the Indian space program captured by your talk just now and the plans for the future, it really makes a very compelling story. We have a few questions, which with your permission, we'll take a couple of them to begin with. So the first question is about why are we not able to make spacecraft that have high load capacity like Falcon 9? As SpaceX is very new as compared to ISRO, still they achieved that feat. What problems do we face to build this kind of a spacecraft?
See, if you look at the first 6 or 7 players in the world, I talked about the current launch capability there. And we should know the history of US, Russia or Soviets, and Europe, China, etc. in the area of rocketry. And this is a guarded area, and we have with our own technology and a little bit of learning from others, we came to this stage and we are progressing. I should say that SpaceX has a foundation led by NASA, who really excelled in this area in the 60s, in the 70s, and they have built upon that actually. So we are not there to compete to make the system, but today the world is looking at how we can cooperate and do different elements for a major mission. Next question. Okay.
So then there's of course this curiosity about the Mangalyaan mission. That was very successful, the first one. Says what about the next Mangalyaan mission? And are we planning to land a rover on the Mars? And how and where?
See, this question should be answered by the current leadership of ISRO. But one point is we can have a mission to Mars only once in 26 months. And current slot is used by several countries. For example, the UAE mission is an orbiter. The Chinese mission has a lander. US is getting ready to have another rover, much advanced. And when we talk about any Mars mission in general, our objective next time should be to have an excellent, scientific, meaningful objective, which require a host of scientific instruments. So the scientific objective should drive our next mission. And the time frame required to develop such instruments and prove them becomes one of the consideration. And certainly in the next 26 months, I would imagine it will not be possible. Maybe earliest possible is 5 years. And we should be working with some of the space agencies to have probably a joint mission in this area. In fact, there is already an agreement between NASA and ISRO signed in 2004 for looking at the future space missions. And I'm sure this Mars community will come for a collective mission in the future, where India will have to play a major role. I would imagine when you look at the planets, we are all one from the Earth.
Okay. That's a good way to say it. And there's another question about, something about futuristic, or probably not so futuristic, about the quantum vacuum thrusters as a, in the development of space engines. And is India doing something? You think if India should do something about quantum vacuum thrusters?
See, what India is doing at the moment is electric propulsion system. So if you look at a communication satellite, there are two types of propulsion systems there. One is to raise the orbit from the geostationary transfer orbit to the geosynchronous orbit. Second one, which should work for several years, is to keep its position, station keeping one. Now, India has used electric propulsion system in two communication satellites for station keeping. And we are developing a heavier thruster for raising the orbit too. Now, the economics comes on the following consideration. Today, a communication satellite, high throughput satellite, is of 6.5 tons. 2.5 tons of that satellite is just a propellants for this initial orbit raising and station keeping. If you can replace this with an electric propulsion system, we save 2 tons. We can launch it with a smaller launch vehicle, and it gives a lot of flexibility as long as we are able to provide the power for the systems to operate. So abroad, people are in this direction. In India too, we are in this direction. So satellite propulsion with electric thrusters, that is going to be the major area of thrust.
So we move on to some non-technical questions now, more on a broader social and economic level. How does, will privatization help ISRO grow the space activities in India? And how will ISRO see these privatization efforts?
See, there are two things. ISRO has been from 1976 working with Indian industry. It has been a stated policy of ISRO saying that wherever industry has a capability, we will not invest inside. They will be our partners. And we developed them, both private and public. And when Mars mission took place, we had 125 of them who contributed to the launch vehicle or satellite or the ground station. Today, it's about 150. So this is part of the process. In that second slide, you saw the number going up. That number goes up because of the industry contribution to the system. That is number one. What has happened to is a next logical step. If you look at an operational launch vehicle, PSLV, or an operational spacecraft platform like IRNSS, or a communication satellite system, there is no reason why the engineers of ISRO should be just get locked onto that production expo. This is best done by the industry. So the PSLVs, the operational communication satellites, etc., provide a big opportunity for the industry. I would say industry, private, public, with participation from ISRO in some. So they can do the production. And the manpower of ISRO can focus on research, development, cutting edge exploration. Every PSLV is important. We have to ensure success. If the entire team is worried about only that, we will not progress. So that's the first and foremost gain out of this system. Plus, there is a lot of energy today, enthusiasm today by the new generation to have these startups. they can contribute in several ways. And if you look at the entire gamut of that $366 billion, 70% come from the space-based services and the ground equipment. A small part in the launch vehicle and satellite. Risk is high, turnover is low in launch vehicle satellites, but when you talk about ground equipment and space-based services, they have a lot to provide. And in fact, these private and public startups, etc., the new community which are getting into it have a lot of opportunities in this area. And ISRO has always been catalyzing and facilitating this process.
Thank you. Now there's one more question. I think in the current climate, it's natural to think of all these possibilities. This question is about, there are threats to humanity not only on the Earth in the form of viruses, but also from space in the form of asteroids. So what is ISRO planning to do, or what should they do to meet this?
In fact, the global space community is worried about this subject actually of an asteroid coming close to Earth. In fact, there was a prediction at least about 7-8 years ago that 2029 Apophis is coming close to the geostationary orbits, and it could give. But our ability, or the global community's ability to predict its movement is very, very limited actually. So when I talked about cosmic hazards, I meant the threat from asteroids, comets, etc., which becomes an important subject for us to understand. That is one. People are also talking about the viruses, bacteria in the migratory process between Earth and other planetary systems. So this is something has to be understood and studied. Astrobiology is important. Bioastronautics, because when you talk about habitat, long life, these are all important. And when we have any deep space mission with the human or without, the cosmic hazard become very important.
So the next one is about, now that India has such a fabulous space program, how do you enthuse the young people to take to space programs in a big way? And what's been going on, and what should be done in the future?
I should say space program has always enthused the youngsters from the 60s to 70s. Maybe in 90s, they were enthused more by the IT boom. Yeah. But with Chandrayaan and Mangalyaan and Gaganyaan, they are back. We don't have any dearth of youngsters. And if you look at the Mars mission, the control room where we had that September 24th, 2014 event, most of them were youngsters. And many of them were ladies. And that's why today we talk about space moms.
Yeah.
So India has that legacy of attracting youngsters. And I'm sure we will be able to get them. And the new startup is another dimension for them.
Yeah, and well, as a last question, maybe, and this question is relevant. I think most of us keep thinking about this too. What makes ISRO so successful? What are the ingredients that ISRO has mastered over the decades to be so successful at such low cost and in such a magnificent manner?
I mentioned about 8 points in the earlier slides. One is the vision. We are very clear about the direction. We don't go back and forth. And that vision is shared by the entire organization. Shared vision, that vision is enriched. Number 2, team excellence. In fact, that is the one which makes ISRO work. When there is a launch, at that point, there will be at least 500 scientists and engineers and another 500 supporting staff working in unison. And nobody need to tell them what to do. They will do what is required to be done. And when there is a problem, a new set of people will come up. And a few thousands would have worked in the background to make that launch possible. We don't worry about the individual getting credit rather than the group getting the credit is more important. So the sigma of individual excellence is much more than the plus of each individual. This is something which is important, of synergy. Then the next part of it is we learn from failures, we learn from successes too. This is another part of it. Accountability. And we want to be always significant and relevant to the country. When there was a drought situation in 87, we all sat together and found out how we can get into combating the drought, what way we can contribute. Even today, that is the thrust of our applications. So we work for the developmental imperatives of the country and make ourselves relevant. And why we are respected outside is because the space systems are making impact for the common man. And we say space is touching the lives of people. This is important through various systems.
Okay, there's also a comment that, would you say a few things about Dr. Vikram Sarabhai's vision and how it's been realized and how his ideas actually seeded the entire program?
See, I should say that Vikram Sarabhai's vision, as spelled out in 1968, has been very deftly executed by ISRO. And we have also progressed further. There are people who say in 1968, he didn't talk about human spaceflight, he didn't talk about going to moon, etc., etc. But that was in 1968. I would say if he were alive today, he would have gone much ahead of what all we can envision.
And well, a few words about Dr. Sarabhai and Dr. Bhabha, how they work together. And
I won't be able to say much about Bhabha's time because I never seen him. I have seen Dr. Sarabhai for at least 7 to 8 months. I have seen about his decision making. A very simple person, if you look at him. In Sriharikota, we had the first sounding rocket launch in 1971. How that decision was taken, at least I was standing there. I was just a few months in the organization. The control and guidance group headed by Dr. Gupta showed to Dr. Sarabhai a control wall, which they had developed to control the rockets. That is important. Then he asked, can we fly this? Dr. Gupta said, yes, if the range is ready, we can fly. He looked at Dr. Murthy. How about the range? He said, we will be ready. And within 2 months, range was ready and the first rocket took off from there. This is a style of decision making. I have heard about the interaction between Vikram Sarabhai and Professor Satish Dhawan, because I call Professor Dhawan my reverential role model. He also guided my PhD. We were sitting in adjacent room for at least 9 years. Basically, I would say one of the key success factors of ISRO is that transition and the respect that they had. Once I heard Professor Dhawan telling he was not ready to take some other assignment given by the government of India, but when Vikram requested me, I joined the commission. And he was there in the Atomic Energy Commission for a small period before he took up this. Another dimension which I have seen is the equation or the chemistry between Dr. Brahma Prakash and Professor Satish Dhawan. This is another thing to learn. Dr. Brahma Prakash was much senior to Professor Dhawan. Of course, they were good friends. But there was a time when Professor Dhawan was the chairman, Dr. Brahma Prakash was the director of Vikram Sarabhai Space Center. I have seen from close quarters how they work with mutual respect, actually. I have talked about it in some of the places. So this is something which we all have to learn, actually. If they were going at cross purposes, just trying to prove that my predecessor was bad and my successors are not good, then no organization would have moved ahead, actually.
Thank you. So I'd like to ask if Professor Ghosh has any comments, questions. Deepak? Deepak, can you hear?
Yeah, now I can hear. It was a great lecture, Dr. Radhakrishnan. We all enjoyed it. And well, I don't have any specific question, but I'm sure others maybe
Yeah.
Some.
Let's see if Professor Trivedi has any comments, questions.
I also want to thank Dr. Radhakrishnan. I also want to say I was very happy to see many questions on the chat. And I know because of a limitation of time, we couldn't get a chance to ask all of them to Dr. Radhakrishnan. So perhaps the Alumni Association can with Dr. Radhakrishnan's permission, find some way that the questions, some of them can be asked to him and maybe conveyed back. But a lot of enthusiasm from many people and great pride, I would like to say, Dr. Radhakrishnan, in ISRO, but also questions, for example, what about microgravity experiments? What about all kinds of things for the future? What role can there be? Someone asked, a metallurgist, what role can there be for me? Someone said, I'm not a scientist. What role can there be for me, etc. So I think a great sort of deal of interest in engaging. Let's see if we can find a way. I do want to share with all of you that, Dr. Radhakrishnan mentioned the AstroSat satellite, which was launched. It was the first satellite India launched dedicated to space astronomy. And Dr. Radhakrishnan was very kind to say, and indeed I feel very proud that TIFR's astronomers played a role in some of the key instruments. But one of the benefits I had was undeservedly, as in my current role, was to be present in mission control at the Satish Dhawan Space Center to witness the launch of AstroSat. And it was really picture perfect. But when I came back, the thought in my mind was, I wish more of my countrymen and women could have this amazing opportunity. And I know now ISRO has built I think it's almost a stadium, right?
Yeah.
And I was wondering, Dr. Radhakrishnan, can you tell everyone what is the possibility if they want to go and witness a launch? Is it possible for common citizens to perhaps put their name and get a chance?
It is possible. In fact, on the website, you can register, and capacity may be around 10,000 people that they can handle in the gallery, where you can actually see the physical liftoff and also on the screen what is going to happen. Like what you saw in the control room, they will be able to see from outside. And people come, they stay, and the launch is postponed, they go back and again come back. This happens.
Oh.
So what I want to say to everybody, especially all the students of TIFR, is you must go and see a launch. There is nothing like that to instill pride, tremendous pride in our hearts for ISRO, but actually for India and Indian science. So this I will.
What I have found is those few minutes of that launch is something special in our life, because anything can happen, from good success to a good catastrophe also.
Usually success.
Yeah.
Well, with ISRO, it's always been a success, as we know. Mostly successes. And
so thank you very much, Dr. Radhakrishnan.
Thank you.
So that's a very happy note to end this lecture. And I want to thank you, Dr. Radhakrishnan, on behalf of the association, all my colleagues at TIFR, all the viewers who have been on the internet and on this Zoom session. And even though, it's virtual, but I'm sure we will clap for you and the sound waves will resound, they will go all the way. And so thank you very much for a brilliant lecture and for making this day so special for all of us. Thank you once again.
Thank you so much.
Thank you.
So I thank all the viewers for joining, and please do send questions to Dr. Radhakrishnan, and we'll collect all of them and pass on so that you can answer them at leisure. And have a very good evening. Thank you very much.
Thank you.
Bye.
Thank you.